functioning and making comparisons to the amphibians. So that when we talk about the amphibians, they have just a moderate amount of yolk, more than a fish, but less than a reptile. One extra embryonic membrane. The time that they spend within the egg is relatively short, and they typically have an aquatic larval state. When you look at the reptiles, they always have a greater amount of yolk. They have 4 extra embryonic membranes. I'm not sure why I have 3 right there. They do have 4. They have 3 more. The period that they spend in the egg is very long, and they do not have the aquatic larval stage. And many of these things that are intertwined, because that extra yolk that is responsible for fueling all of the changes that take place in the egg, thereby, not delaying, but thereby avoiding that aquatic larval stage. Right? So in the tadpole, they hatch out and they start feeding. But all of those extra changes in a reptile take place in the egg, so they have a much larger amount of yolk. The extra embryonic membranes presumably make it a little bit easier to lay that egg on land compared to a fish or an amphibian that always, of course, is laying it in the water. So we did look at the cleidoic egg, the structure of it. It's something that you find in all amniotes. You're going to find it in the reptiles, the birds, the egg-laying mammals, and even in the other mammals, we have a modified version of the cleidoic egg. We do have the yolk sac, just like the other groups do. That's the one that we share in common with the fish and the amphibians. It's well vascularized, and it's important in digesting, providing digestive enzymes that break down the yolk, and then the nutrients are transferred back into the embryo by the circulatory system, which is why it's well vascularized. The Allantois also is well vascularized. It's going to function as a nitrogenous waste storehouse. So it's really like the terminal end of the cloaca grows outwards. And so as this nitrogenous waste comes through the system, it just gets stored in that sac. It too has a very good blood supply, and it's involved in gas exchange. So it's often up against the chorion, up against the outer part of the egg, and so it'll have additional oxygen diffusing into the blood of the Allantois and then back into the embryo. The chorion does a little bit in gas exchange by default just because it's the most external of the membranes. When we look at patterns of reproduction, the reptiles are oviparous, and they do have internal fertilization. That internal fertilization, though, is accomplished in a number of different ways. Hemipenes, a penis in the crocodilians and the turtles, and then cloacal apposition in the tuatara, a sphenodontid, most primitive of the living reptiles. And then the other things you see on there are things that we're going to get to today. So epidermal scales, dermal bone, respiration by suction, uric acid instead of urea, and then temporal openings. I think we'll have time that I'll move on to snakes. We look a little bit more in detail at the anatomy and functioning of snakes just because they're weird compared to most other terrestrial vertebrates. Any questions on last time? All right. Okay, so we'll say a few things about the skin of reptiles. Compared to an amphibian, the skin of a reptile is really dry and virtually waterproof. So what you're going to find is many more layers of cells in the epidermis of the skin of a reptile. And you're going to find a well-developed stratum corneum. Okay, so we saw the beginnings of the stratum corneum in the amphibians, a layer of dead cells on the outside that helps minimize or lessen in any way the amount of water vapor that's being lost. But in a reptile, you really see many layers of dead cells filled with keratin. And if you think about it, it makes sense. Why is it dry and virtually waterproof? Well, these are totally terrestrial animals, and they are no longer using their skin for respiration. So in order to avoid water loss in that dry terrestrial environment, they're trying to make the skin as waterproof as possible. Going along with that is that skin glands are virtually absent in reptiles. Right? So we have poison glands and mucus glands, remember, in the amphibians, but now they're virtually gone in reptiles. There are some, a few, but they're not widespread, and many species don't have them. When they are present, they're usually scent glands. They're releasing a chemical that is communicating to other individuals. Could be a male communicating with a female, could be one individual communicating with others, other species, other males, for example. Another thing about the skin is that it's just not a flat epidermis, as you all know. So you're going to get that surface thrown into folds. So this is your epidermis, and then this is your dermis down in here. We're going to really harden that area, and it's going to end up forming the reptilian version of scales. So we're taking that outer layer of the epidermis, filling it with keratin, dead cells filled with keratin, making it hard, and that's going to be the scales that are overlapping. Right? We're throwing it into these folds. Reptilian scales differ from fish scales. They're not homologous structures. So in a fish, scales develop from the dermis. But reptilian scales, and those in birds and those in mammals, are derived from the epidermis instead. So they're not homologous structures. Since you do have this dead layer on the outside, that's a perfect breeding ground for bacteria and fungi. And so you'll find that all reptiles are going to shed that skin periodically. Now the snakes will typically do it all at once, and so you get that big, long piece of dead skin that looks like a snake. Lizards generally do it in many pieces. There's many patches of skin that are falling off. And alligators and turtles usually do it by individual scales. And so it's not coming off in big pieces. It's not coming off mimicking the entire animal. But they all will shed that outer layer periodically. Right? That's to accommodate growth to a certain degree, but also to get rid of that dead material on the outside. So reptilian scales are epidermal in origin, but reptiles still do have some hard structures that are derived from the dermis. And so in that sense, they would be homologous to the scales of fish. And there's three different types of hard structures found in different groups of reptiles that are derived from the dermis, not the epidermis. Oh, which one should we put up first? Well, the one that you know the most, and that would be the turtle shell. The bulk of the turtle shell is made up of bone. I don't know if we covered it in here or not. I don't think we did. There are two different kinds of bone. There is bone that forms within a piece of cartilage. That would be like your humerus was formed that way, your femur. Most of the bones in your body are formed that way. There's a piece of cartilage that is there early in your development, and then gradually that cartilage is replaced by the harder substance called bone. But there's another way in which bone can form and that is it can form within the dermis of the skin. So you can have dermal bone as opposed to cartilage replacement bone. The shell of the turtle is dermal bone. Now, when you see a living turtle, what you're looking at are the epidermal scales on top of the dermal bone. So that if I pass this around, this is just, I believe it was from a painted turtle, maybe a red-eared slider. And you can see the boundaries of the bone, but you can also see the boundaries of where the scales were. And they don't necessarily match each other. Okay, so the deeper, whiter markings are where the scales were, and then you can see lighter brown markings, and those are the junctions between different pieces of dermal bone. And I don't know who this is. It's been here 100 years, but it's a turtle skeleton taken apart, and you can see all of the individual little pieces of dermal bone that contribute to the shell of that particular animal. So we can get bone forming in the dermis of the skin. Reptiles have 3 different examples of that. One's the turtle shell. 2 is something called gastralia. And 3 is something called osteoderms, and like an idiot, I forgot my book with the photograph of osteoderms. Okay, so what are gastralia? You'll often see gastralia referred to as abdominal ribs because they look like ribs that are along the abdomen of crocodilians. Sphenodon has them as well. Okay? But they are dermal in origin as opposed to typical ribs, which are cartilage replacement bone. I'll pass this guy around, and you can see his ribs up along the standard rib cage, but then look back along the abdomen, so resting up against the black wood, you'll see a bunch of rib-like structures. Those in reality are gastralia. Those are pieces of dermal bone. Osteoderms, you can see the word osteo for bone and derm for skin. These are just little flecks of bones that occur. Not all lizards have them. Many lizards do, and crocodilians will have them as well. That's a lizard. Okay? They're just in the little flecks of bone in the dermis of the skin of that animal, presumably for a little extra protection. But I don't see how they offer very much in the way of protection. So those are osteoderms, crocodilians, and some lizards. I did forget an old textbook that has very good X-ray photographs of 2 different lizards, one which has osteoderms and one which does not. It's real obvious when you look at it. I did want to say one thing. I missed it about epidermal scales, and that is that in a lot of reptiles, those scales can get modified into structures that you might not think are made from scales. So one of the jars, for example, I think we have horned lizards that are out, right? And they look like they have little horns up on their heads. But all those are modified scales, epidermal scales. Another example of modifying epidermal scales would be the rattle of a rattlesnake. So these scales can take on rather complex shapes. So that might be the shape of